Thanks everyone for joining. So my name is Matthew Hart. I'm the founder of a company called Soter Analytics. We work in the health and safety space, specifically making wearable technology. But I'm not going to talk a lot about that on this webinar. Instead, I'm going to talk about how I'm a reliability engineer and how I actually started the company based on reliability engineering techniques. Again, not talking much about the company, but why I think these techniques are useful, why they can be applied for helping humans in their jobs as well, to avoid breakdowns, to not get injured. So run through a number of different engineering techniques for the group. And then at the end, we also have the opportunity to do a question and answer. So anyone can ask questions throughout the webinar. And then at the end, I'll look through them and I'll answer as many as I can. So a quick agenda of this meeting, of this webinar. So I'll talk about my background. I'll explain what reliability engineering actually is. We'll go through a number of concepts. I think there's 5 concepts to go through. I'll explain how they work for engineering, and I'll explain how they can be applied to humans and workforces as well. Being an engineer, sometimes I run the risk of treating everything like an engineering problem, but people are not machines. So point number 4 on the agenda is actually going through why they're not machines, what's the difference between machines and people. And then right at the end, I'll spend about 2 minutes around the company itself, how we're using these engineering techniques and how we're helping people avoid getting back and muscle injuries. So this is what I looked like back in 2010. It was my first day working for BHP. I worked up in the Pilbara region. I ended up working for BHP for 5 years. I was working for a mining company before that as well. Again, I don't have a health and safety background. I'm a mechanical engineer. While I was working for BHP, I got my master's in reliability engineering as well. I left in 2016, and by 2017, I had an MBA. And then I started Soter Analytics. So that's a really quick brief of my background. So what is reliability engineering? The definition I've written here, it's describing the ability of a system or a component to function. If I simplify it or I turn it into other words, reliability engineers were always focused around stopping the machine from breaking in an unplanned fashion. So the worst thing that can happen is an unplanned maintenance. Basically, you have a machine, you need it to produce something. If it's in mining, you need it to dig ore out of the ground. If it's an aircraft, you need it to transport passengers, or at least you used to. And yeah, basically, if this machine stops, you don't get the production you need out of the machine. Plus, you need to spend a lot of money on fixing it in an unplanned fashion. So when we were working up in Newman, I think we had it like 6 or 7 weeks in a row that we were ready to fly back to Perth. And the airplane, the Qantas airplane would come, it would land, they would find a fault, and we weren't able to get back home. What Qantas needed to do, because this was an unplanned maintenance event, Qantas had to actually fly engineers from Perth to Newman, fix the plane, which usually I think is just like replacing a light bulb or something quite minor. And then by Saturday, so we were due to fly out on Friday, by Saturday, this plane was ready to take people back home. So firstly, you don't have the plane to produce what you need it to do. It's really expensive to fly people up to fix it because it was unplanned. And you got a whole lot of unhappy fly in, fly out miners as well, which was not great. So it's a bit of it's clearly not what you want to happen. So if we look at reliability engineering, we want to try to avoid those events. We want to stop bigger things as well from happening. You know, we don't want an aircraft failure, for example, because that's even a bigger problem. So what do reliability engineers do for an airplane? In the design phase, everything is tested. Wings, I have the example here of a wing, so they're comprehensively tested in the design phase. They go through many cycle tests to simulate what's going to happen to this aircraft wing over 1 year, 5 years, 10 years, over the lifetime of the airplane. And they want to make sure that, okay, we're going to build a wing, we're going to make it out of a certain material, and we want it to last for as long as we need it to. What else do they do? Well, we work out how often aircraft engines need to be serviced. So unlike a wing that's going to last the lifetime of the aircraft, engines usually don't. Losing an engine, obviously bad. there's components in an engine that last actually less time than the engine themselves. So they need to be replaced or serviced, oil needs to be changed. So aircraft engines, the reliability engineers have determined that every 600 flight hours, these engines need to be serviced. Now, you think like there's still some old 747s flying around, but they have a very clear end of life date, even if you take economics out of it. So a lot of them are being retired at the moment for economics, but a 747 can do 35,000 flights before it has to be retired. And the reason it has to be retired is actually back to the wings and the chassis. When they went through their testing, they got to 35,000 flight cycles before they started to see that the failure rate started to increase. And they say, okay, like we will retire this aircraft at 35,000 flights, no questions. So you can see, like, as reliability engineers, we spend a lot of time, a lot of focus on making sure that these machines don't break, and we're very, very preventative. When I was working for the mining company, I was looking at health and safety, and I thought there was a bit of an opportunity because how we were protecting our people was a long way behind all the time and effort and resources and smarts that we were putting into how we protected our machines. So much so that I came up with this sort of statement that doing a bit of analysis of what reliability engineers were doing 15 years ago, that's what I think health and safety generally is doing today. We're 15 years behind how we protect our machines. We're quite reactive, we're not preventative, predictive. So there's a 15-year gap. And I want to talk to you through some of these techniques that we could potentially use to bridge that gap. So concept one that I want to share is the engineering technique called the bathtub curve. So what we have here is a graph of machine failure rates. So we've got here on the y-axis the failure rate. So as you bring a new machine or component or piece of equipment into your production line, you have what's called the startup commissioning phase. So this is early on, it's a new piece of equipment, it's just been manufactured, it hasn't really been tested and run in and checked if there's any problems. So startup commissioning is actually the period of time where you're likely to see failure rates of a machine. Then that machine becomes, you start using it, you fix all the little things that have gone wrong, it starts to work more normally, and then this is called the useful life period, where the failure rate actually is quite low and quite steady. And then you get to the end of the lifetime of the machine. So things start to fatigue, seals start to get old, you're starting to replace more and more things, and this is called the normal wear out period. So as you get to the end of the life of the machine, it starts to creep up, the wear out curve starts to creep up, and eventually either a failure happens, or as an organization or a business, you say, okay, now the risk is too high of a failure, we will replace this with a newer piece of equipment. So in real life, what does this look like? So if you're buying a car, I think we have a law actually in Australia, it's called the lemon car law, so lemon law. I'm sure we've all seen on like Today Tonight or Current Affair or whatever those stories are, where, the poor family who's bought a car, they've spent $40,000 on it, and it's just a piece of shit. It doesn't work. Things are breaking. You can tell that there's something fundamentally wrong with this car. So what's happening actually is this is what's called the startup commissioning phase. Most cars are fine. No failures in the startup commissioning phase. Some, for some reason, just manufacturing faults or things just aren't working as designed, and you've got a lemon car. Then you get to you get through that phase, you keep running it normally, you service it. There's not a lot of servicing required. You get to the end of the lifetime of the car. I've got a quite extreme example here of a rusted out car, but things start to rust, seals start to break, things start to go wrong. It starts to get less efficient as well, and you say, well, I'm going to replace this with a new car, and then you risk the lemon car as well, but you get through that stage, and sort of that's a real world example of the bathtub curve. Now, if we apply this principle to people, if you get a new worker into your organization, actually right when they start is when you can expect that you're going to find out how this worker performs. Are they going to get injured or are they not? Are they up to the physical demands of the job? Are they not? So this person is actually in the new worker phase or the startup commissioning phase. They're not work hardened, they're less experienced. I'm sure anyone who's worked like a physical job, I did throughout university, you know this phase very well. And it actually takes you a month to 2 months, at least it did for me, about 2 months to get through that phase. Then you become work hardened, and then most of your workers are sitting in this, normal phase. Nothing going wrong, they do their job, it's all good. Then we start to get a little bit older, so we start to age, and then remember the example of a little bit of rust or one of your seals starts to bust. So we start to get into the aging worker phase. So this is the normal, what I would call the normal wear out phase. So they're getting weaker, they're getting less capacity, and their possibility of getting injured actually has increased. So a couple of strategies we can put in, very similar sort of strategies to what we're using in engineering. So testing the worker before you hire them. So a lot of companies are doing functional job testing. So I think in Australia we call it, I think we might call it pre-employment medicals. Functional job testing. So we understand the physical demands of the role, and we create a test, or with our medical partners, we create a test that says, look, when we get a new hire or before we hire them, let's try to estimate the probability of this person to be able to physically do the job. So the more you can, I guess, filter out people who you are just physically not going to be able to do the job, the lower injury rates you're going to have for that job position. The second strategy that you can put in place is just really high quality new starter training. Train them on what is the right way to do the job. Really focus on the physical demands of the job along with everything else that you need to teach them. Perhaps buddy them up with someone, with more experience. There's quite a few things we can do for once you get the worker onto the job site to actually coach them through what we call this startup commissioning phase. And then we get to the aging workforce, which in Australia and the world, actually, we're all facing. Our workforce are getting older, aging. The number one technique here, I think, is early intervention of pain. So the more you can encourage an early reporting of a problem for a worker, making sure that they understand that as a company, you're actually going to support them through this. You're actually going to do something about it. You're not going to find a way to, manage them out of the business. Don't do anything crazy like that. Encourage early intervention, because back to the car example, imagine you have the red engine light come up on your dashboard. Are you going to ignore that and just keep driving? Because this is an early intervention of an engine problem. Are you going to keep driving, and then your engine blows up, you're stuck on the side of the freeway and go, oh, maybe I should have done something about that? No, you're not. You're going to take it pretty quickly to a mechanic and you can do something about this engine. You can do the same with people. There's a huge advantage in that people are your sensors. They can process what their body is feeling, what is it doing. They can work out potentially if they're going to start to have a problem, if they feel like something bad is starting to happen. The negative is getting them to actually tell someone about it. With a sensor on a machine, you can just, it's a bit of code, it's a bit of programming, it's not that difficult. With a person, really encourage them to let you know that something is about to happen. And if you can do that, then you can do something about it. The second strategy that was like been going around forever is you can use their experience into new, less physical roles. So people eventually, certain people at least, they migrate into management roles or more specialist roles, so that the younger people in your workforce, the more physically able, they can do the more difficult, physically demanding jobs. And the older people with a lot of experience can actually use their experience and less reliance on physical demands. So the second technique I want to talk about is what's called the Pareto rule. So this is called, the summary of this is 80% of something's effects come from 20% of the causes. And I'll give you a little example. So again, back at BHP, I was working on a project to analyze what was happening to these excavators. So for those, I think most people in Australia know, but excavators are digging the ore, they're putting it on trucks. So I looked at a whole year of these breakdowns of the excavator fleet. And what we had was one event that caused 400 hours of downtime. So this is a multi-million-dollar breakdown. What happened was the boom, so the thing here that connects the bucket to the chassis or the cab, the boom had a crack, and you've got to do something about this crack pretty quickly. You've got to repair it, because if you don't, the whole machine's going to fall apart eventually. So we had a boom crack, 400 hours of downtime. Clearly this is not good. But then we looked at, okay, what are the other failures that are happening? So this machine had a lot of starter motor failures, 54 actually over a year. Each failure itself, 1.2 hours. So this sort of gets lost 1.2 hours. It's not great. Shutting down your machine for an hour is not great. But if it happens once, lots of things happen once. You're probably shutting down a machine 1 hour every couple of days anyway for things going wrong. So if you talk to the maintenance crew or the fitters, they might not actually realize that, this has actually happened 54 times. What did tell us though was the data. So we recorded obviously all the breakdowns, the detail, what happened, what went wrong, what needed to be replaced or fixed, how long it took, 54 times in a year. So this equated to 65 hours of downtime. And then everything else that went wrong with this machine, 100 hours in the year. So as an engineer, I have limited time, and we can't really be fixing or worrying about every little problem. So if we had focused on this 100 hours of things, these random things going wrong, and you fix 1 or 2 of them, yeah, okay, great. Maybe next year you save 2 hours, 3 hours, 4 hours. But clearly where I needed to be focused was the 54 starter motor failures. If we could get rid of them or half them or reduce a large percentage of them, again, we're saving multi-million-dollars for the company. So this project was actually quite successful. What it turned out was they were shutting down the engine when it was hot, and then they were trying to start it up again when it was hot. This just caused too much resistance for the starter motor. Now, when we were doing this project, we actually had quite a number of different people involved. We had engineers, we had maintenance people, we had health and safety people as well. Nothing against the people in the room. They thought they were making the right decisions, but the health and safety suggestion for an improvement was, okay, 54 times we have to replace these motors. It's quite difficult to get into the engine bay. They're quite heavy. Someone came up and found, okay, we can actually buy a starter motor that is lighter, so that when we're changing it 54 times, this lighter motor, we can take it in and out much more easily. Yes, it had a little bit less performance, but it was lighter. So, this is actually solving the problem. I'm going to talk about root cause in a minute, but this didn't solve the problem, because the problem is 54 starter motor failures. The reason for that, as I said, like the motors just weren't the right specification for the way we were running them. The solution was actually a much, much, much heavier starter motor. Yes, if we had to change it, clearly, heavier, we needed some additional tooling. It took a lot longer actually to replace it as well. But this new motor didn't fail. So you're actually eliminating the problem full stop. So when I talk to a lot of health and safety people, sometimes the trap that I can see happening is they focus on the noise. They focus on what people are telling them. They're focusing on the issue of the day. They're doing a lot of reactive stuff as well. So if someone got injured for a cut hand, we need to do everything we can to stop the people cutting their hand. Someone had that last week. This is our biggest problem. We really need to fix that. Not saying you shouldn't, but perhaps in addition to that, think about the Pareto rule as well, and look at everything from a holistic point of view. To be able to do that, make sure that you're recording data very accurately, because if you don't have data, you can't actually do this sort of analysis. So my tips here is like record the time lost for each event, the cost of it, the severity, all that sort of stuff. The more data you can record, the better. Once every half year, maybe once a year, analyze your data, group them all together, figure out what's happening frequently, what's costing a lot of time, what's costing a lot of money. But don't just treat it as a machine, because point number 3 here is be really aware of the severity. So back injuries, we all know, like, they happen frequently. They're really, really expensive. You need to avoid them at all costs if you can. But they don't kill people. So you're going to have this huge cost, this huge frequency, but falling from heights actually kills people. So clearly that is just an unacceptable. All injuries and fatalities clearly are unacceptable. Fatalities, there's no going back. So this is where the Pareto rule might not work as well for humans as it does for machines. If a machine breaks down and you lose the machine, yeah, that sucks. It'll be really expensive. It'll show up in your data as being really expensive anyway. So you'll put some focus on that. Unfortunately, if you lose a person, it's actually not going to be as expensive as a back injury, a serious back injury. But there's a whole other thing, clearly another reason we want to avoid that. So Pareto rule is good. Analyze your data, record your data, analyze your data, but just remember as well that there's a severity when it comes to humans that doesn't exist for machines. Okay, so probably my favorite, root cause analysis. In engineering and in health and safety, the engineers or the professionals or the health and safety personnel, we spend a lot of time doing root cause analysis. You might have heard it RCAs. There's a whole number of different techniques, but basically you're trying to figure out what caused something and how do you stop it from happening again. Root cause analysis is a really clever way of thinking about a series of events that might have contributed to something going wrong. The example I give of that, so the Apollo 1 fire, I've been listening to some podcasts lately. They did this great BBC podcast on, it's called 13 Minutes to the Moon, where they talk about firstly the trip to the moon, and I think the latest one is Apollo 13. So in that journey of explaining what happened with NASA, we had Apollo 1. Now Apollo 1 blew up on the ground, killed all the astronauts. Clearly not great. And when they did their root cause analysis, they found that quite a number of things happened to cause this event, this tragedy from happening. So to summarize it, I'll go through the failure modes that they find. So they found that the hatch took 5 minutes to open. So in emergency, 5 minutes, usually that's too long. The second problem was inadequate insulation. So they had electrical wires running through this machine, running through the cabin. They weren't insulated. And I think what happened was 2 caused a spark. So 2 got too close together or rubbed or some sort of spark was created from not having insulation required. They had combustible materials in the cabin, so things that could burn. They were pumping pure oxygen into the spacecraft. They actually changed that after this event. So pure oxygen is the perfect thing that a fire needs or explosion needs. So they actually changed the balance going forward so that if something happened in the future, a spark, that maybe the pure oxygen wouldn't be so combustible. And they had no one on the ground ready to do and rescue them in case of emergency. So they're sitting on the ground, they're not in space, they're not in the air. Everyone unfortunately thought that, well, nothing really can go wrong, so we don't need a rescue crew. Now, root cause analysis, they came up with these 5 and probably heaps more, but they came up with these 5 different things that went wrong. The sad thing is that if one of these things didn't happen, the tragedy likely wouldn't have happened. So when you're looking at like an event of something that went wrong, don't just think like, okay, one thing went wrong, how do I stop that one thing? Very often, and especially in complex failures, multiple things went wrong. And if unfortunately the NASA engineers, if they had thought about this potential scenario, and now they do, they would have put controls in for all 5 of these things, and the failure definitely wouldn't have happened, but just one of these things and it wouldn't have happened. So it's an example of like a complex root cause analysis. There's a simpler version. It's called 5 whys. So I think every engineer I know has been taught this. Everyone, we get it drilled into us. It's a simplified investigation tool that helps find a single root cause. So basically how it works is you keep asking why. I've got a 5-year-old son. I'm sure heaps of people have children. And when they get to that toddler age, why? It's actually quite clever of them, because they're actually trying to figure out, okay, why? Why is something actually happening? I'll give an example. It's a made-up example, but we've got a worker who slipped and fallen and suffered an injury in the workplace. And the why, what did he slip on? Well, there was a puddle of oil on the floor. So to me, like, thinking about it pretty simply, if that puddle wasn't there, great. Why was that? We need a cleaner to clean up that puddle. If there's puddles of oil on the floor and we have a cleaner running around, then we're going to stop that from ever happening again, right? Because no oil on the floor, all good. Well, firstly, the cleaner can't be everywhere, but anyway, all good, problem solved. But then you say, why was there a puddle of oil on the floor? For example, it's spilt from a compressor. So a compressor had a leak, it started spilling oil. Why was it spilling oil? Because it had an oil leak and it was not detected. Why was it not detected? This compressor isn't on a maintenance inspection schedule. So no one's tasked with actually checking this compressor, or any compressors actually. So this compressor had an oil leak. What about the other 20 or 30 or 50 or other 100 machines you have in that area or on your work site? And the 5th reason, as I said, not in the maintenance system. So that's the root cause of this incident. It's not that we need a cleaner and the cleaner didn't clean up the puddle of oil. The root cause is we've got machines or equipment in our workplace that are not on a maintenance schedule. So when I look back at, like, as a safety professional, you can always be reactive. So if someone slips, how do we stop that? How do we hire a cleaner to stop that from happening again? Or you can be proactive and say, I've got machines in my workplace, or whatever the reason is. I've got things happening that is more than just this one incident, that if I fix all those, if I put something systematic in place, I'm going to stop all the other injuries that I can't predict. I can't predict what people are going to be injured from, but I can predict where the risk comes from. So this is called 5 whys. Basically, the principle is ask why 5 times, and you usually get to the root cause. Okay, predictive analytics. As I explained right at the start, we have machines that we spend millions and millions, and probably as an economy, billions of dollars eventually on actually predicting and stopping them from breaking. Predictive analytics takes historical data, applies analytics techniques to predict a future outcome. So if we go back to our airplane, we've got the historical analysis of when that airplane was being designed. They were testing the wings, the chassis. They test a whole lot of things. They're looking for fatigue cracks. They're looking for things that go wrong. They were trying to work out the strength of the material. They're trying to look at where the weaknesses in the materials are. So for a 747, testing over a long period of time, they speed up the testing. They don't do 35,000 flights. They replicate 35,000 flights, or they call them pressurization cycles. And they show that when they get to 35,000, that the quality, or let's say the capacity of the material, starts to weaken to a point where we just need to replace the aircraft. We need to stop this. We're getting to a period of risk which is unacceptable. For aircrafts, this unacceptable risk is super low tolerance, so they don't tolerate any risk, basically. 35,000 pressurization cycles, and then we're scrapping the machine. So as someone who does do a lot of flying, I'm like, okay, great, 35,000 cycles. What happens before 35,000 though? I'm sure we're not waiting for 35,000 flights before, and we see if we don't check the wing. Let's take a wing as the example. We're not checking it because we know 35,000. It'll be good, and we don't need to worry about it until then, till we scrap the machine. Now, when they're making the machine, when they're making the wing, things can go wrong. When they're mining the material, the quality of the material can be slightly off. Many things can go wrong. So waiting for 35,000 pressurization cycles is a bit of a recipe for failure. So then we get into condition monitoring. What they do is they take the machine, the airplane, out of service and out of production service, and they actually do a maintenance service on it. So they do that frequently. And on this frequent maintenance service, one of the things they need to do is condition monitoring. So they test for cracks. Because if you can start spotting minor cracks, which are unusual, cracks are usual, but if you find something that's happening unusually, then you say, okay, I'm about to have a problem. It's a bit like your check red engine light on your car. You know, you're about to have a problem. So this is great. We're not waiting for 35,000 flights anymore, which is cool. We're seeing problems before they turn into big problems. That's good. We can do something about it. That's good. We can stop the aircraft wing from falling off. That's good. What happens between testing? Now, in aircrafts, again, this is quite a new development, but what they're actually doing is they're putting sensors on the wing itself. We're actually building it into the wing to check for micro cracks in real time. So as an engineer now, I'm not waiting, if I'm the engineer that's responsible for the service of this aircraft, I'm not waiting for once every 3 months or whenever they do the periodic testing, but I'm actually getting real-time data come to me. And it's, you know, I can start to see a problem as it's happening, if something's happening. So there's a number of different things that the engineers have put in, a number of different techniques that we can use to stop the failure from happening. We can do the same for people. And I think what we are doing for people, lots of companies, lots of startups, lots of tech companies are building the predictive analytics for humans. So if we look at the historical analysis to start with, this is what you can do today if your data set's good enough. It goes into the Pareto rule that I talked about before. So get your data sets, segment them, work out which groups are under higher risk than others, which ones are getting more injured than others. You might have 10, 20 years of data, or probably not 20 years, 10 years of good data that you can use. So use that, work out where your problems might be. And then in parallel to that, think about the future as well. So build data sets with smaller granularity. And what I mean by that is a lot of data sets that I've seen, we've worked with some really big companies that have shared their data with us. The data sets we see are events. So when someone reports an injury, how long did that injury last? How much did it cost? What was done? All that sort of stuff. But think like, okay, that's good for now, but how do I make a smaller granularity data set? How do I find out when people are feeling pain? You know, then that's a bigger data set. I can do more cool stuff with that. So what I've come up with here is a sort of 3-step process. So measuring injuries is okay. Measuring the report of pain is even better because it's more granular. Measuring the events or movements that cause the pain is the best. Very often, to build these data sets or to understand how it works, I'm giving a very high level overview at the moment. So work with experts that can train and help you use your data sets. I think everyone on this call probably works with engineers in the business as well, or even better if you've got data scientists, but they might be a little bit too specialized. Sit down with an engineer and say, hey, like, what would you guys do? Like, explain this data to me. How would you analyze this data? Watch YouTube videos on how to analyze data. Become proficient with Excel if you're not already. But sit down with an engineer or someone who's really Excel and data savvy and explain what you're trying to do and see if they can help you. If you can get to the point of measuring activity levels or events or movements that cause pain, then you're going to be best in class in your field, really. Like, the world is becoming data-driven. It is already. It's becoming a lot more. If you can start getting those data sets and then analyzing those data sets, you're going to be in huge demand. You know, if you come in and say, I'm a data-driven health and safety person and here's what I do, you're going to be in huge demand. Predictive models are a really highly specialized field. So when you get to the actual prediction of injuries and pain and that sort of stuff, you can do certain elements of it yourself. You might, as I said, want to sit down with an engineer. You might want to sit down with a company or something like that, a third party that can actually help you through it. Now, condition monitoring. You're probably wondering, like, as I'm talking predictive models and collecting these data sets, okay, scanning people, taking them out of service, figuring out if there's something going wrong with them, that's not really feasible, right? Like you can't take a worker out every 3 months and do a full body scan and MRIs and X-rays and figure out what part of their body is breaking and what's not. So it's not very feasible. But for machines, we need to do that. And the reason is machines don't talk to us. We need to figure out what's going on with that machine. We need to scan it. We need to do all these sort of things to figure it out. But people have a huge advantage. They do talk to us. And this is back to my point of build an early reporting culture. If you can explain to your workforce why it's important to notify someone about an early incident or an early pain, then you can do something about it. If you know about it, you can do something about it. It's probably really hard to do this, to build this. Hard because it's important. It should be done because it's important. It's also hard because it's important. So you need to remind the workforce, that's my tip. So explain to them what early reporting is, why it's important, how to do the reporting, what happens after they do the reporting, how you're going to support that worker. So if you can build that, then what early reporting actually helps you identify is the start of the wear out curve. Now, wear out curves don't necessarily need to happen at the end of your working life. It's not the end of the world sometimes. You know, it's not, you know, that you can't do this job anymore. Sometimes you can replace something or a certain movement pattern or change the job in some way, or even just build up your physical fitness. There's things that you can do. It's like when you have a problem with an oil filter, you don't throw the car away. You know, you fix the oil filter and then you're good to go again. The car keeps working like normal. It's the same for people. There's things you can do. You can build a maintenance or repair strategy for the person, but build the early reporting culture, because without that, you're going to really struggle to predict anything. With that, you're just going to be best in field, best in class. Then we get to sensors. So when the people aren't able to explain or still don't explain that there's a particular risk that you have, sensors can help. So I believe that sensors will be the biggest step change. They already are becoming the biggest step change in reducing injuries that we'll see in all of our careers. And the reason I know that is because it was for machines. It's the same. If we look at a truck that was produced, a mining truck that was produced 20 years ago, you know, it probably had a few sensors on it. If we look at a truck that's produced now, it's got 10,000 different sensors on it. If you look at the reliability of a truck 20 years ago, nothing special. If you look at it now, they run themselves, they run forever, they don't break down very, very often. So we've seen the step change that predictive analytics has done for machines, and the stuff that we're able to do with the data. We're able to build better trucks, more fit for purpose trucks. We're able to see when something's going wrong with the truck. You know, it's a huge game changer. We can do the same for people. So what can sensors do? It can identify trends and problems well before you as a safety person will know about it, but even before the worker themselves knows about it. We can collect these data sets that I encourage people to do, you know, more granular, bigger data sets that you can build better predictions off. There's another big advantage is that you can actually engage the workforce through sensors as well. So if you have sensor technology in your workforce, or even if you just look at early reporting and you take the sensor out of it, if you can engage the workforce to report early, you're gonna build a safety culture within that group. They're going to start coming up with suggestions. They're going to start thinking about why things are happening. They're going to, you know, it's just going to be a way better organization, a way better culture within your organization. And then you add sensors on top of that, where if you can feed the information to them in a certain way and let them work with their own data, it's super valuable. So I've talked about why people are like machines. I want to talk about why they're not like machines as well, because there's some really key differences. If you have something go wrong with someone's knee, you can't just change the knee. You can, but you can't, that person is never going to be able to do the job again. It's a huge problem. Like, you just can't replace parts or components on people. So like machines, you can change an old one with a new one. With people, I mean, you can, but you lose the experience. It's a huge impact on the person. It's not great for the culture of your organization. So let's just say that you can't replace old people with new people like you can a machine. With a machine, there's no emotion involved and no loss of experience or anything like that. Again, machines can be programmed or operated in a particular way. Humans can as well, but I'm not sure that you always want to do that. We have a free will. We like our own free will. We like making our own decisions. It's actually our advantage. So if you lock everything completely down and say, this is the only way you can do everything, sometimes you need to, processes of work and stuff like that, lock things down and say you must do it in a particular way. But if you run your every single task and everything like that and say there's only one way to do everything, you're going to have a pretty annoyed workforce, I think. So we have a free will. We like it. It's actually our advantage as well, because we're able to solve problems on the fly, which very often a machine can't do. We've got to program or operate it in a certain way. We also have the ability to improve and repair ourselves. It's a huge advantage. Like, if you get a crack in a wing, the plane isn't going to fix itself. If you have like muscle soreness, and you can the person themselves knows how to do the stretch or the job hardening or just the body conditioning, that they can repair that muscle soreness themselves, it's a huge advantage. No machine can fix itself. We can. So I want to explain for maybe 5 minutes, I guess, why we use these reliability engineering techniques to start my company, Soter Analytics. So I will try not to sell anything here, but I just want to show how we put these principles, these reliability engineering principles, in place, and what we're trying to do with that in a health and safety setting. So it's a real world example. So we created the company about 4 years ago now, and we created it to reduce what we found was the biggest and most expensive injury problem. So back to the Pareto rule, the pretty frequent and clearly the most expensive injury type is musculoskeletal injuries. When they happen, they take ages to recover from. A lot of people, unfortunately, never recover fully from them. They have a huge impact on your social life, your personal life. So we saw, okay, this is a huge, big problem we need to solve. I'll talk about it in a sec, but we can solve it using a number of different engineering principles. And the third thing is that was super exciting about the project for me was we can actually engage the worker. Rather than just telling the person what to do, we can actually take them on the improvement journey along with us. So this is our little wearable device. I don't have one with me, unfortunately, but it's a tiny little device. It's worn on the back of the worker's shirt, and it's measuring all the movements they make throughout the day. So every time they bend or twist or put some sort of force on their upper body, the device picks that up. So when we're talking about granular data sets, okay, we're not waiting for an injury, we're not waiting for pain. We're picking up 10 or thousands, if not tens of thousands of events every day from the person. Now, not every bit of data is useful, but we try to work out what is useful. And the useful event that we've come up with for the worker themselves is if you do a particular movement that is hazardous, and by hazardous I mean has an increased risk of causing an injury, we actually warn the worker. And how we warn them is the device itself beeps and vibrates. So an example of this is if you lift something heavy, I'll use the boring example of lifting something heavy with a bent back and you put all that force through the body. Our device is going to pick that up and it's going to beep and vibrate and let the person know that probably not the greatest movement they can make. We've got heaps of other movements as well. So twisting movements, so picking something from racking, putting it onto the pallet, pallet jack or whatever they're using in the warehouse. We're picking up vibrations. We're picking up all these different movements. We clearly, I would say, like clearly best in class in measuring the different events, what they are, and actually accurately giving an insight back to the worker. So we got more granular data sets. We're engaging the worker on doing something about it because they actually work with this feedback. So if they get the beep and vibrate, they know why. We explain why they're getting that. And then they start making behavioral changes. If we look at these hazardous movements, so HM per hour is actually hazardous movements per hour. So, and we look at all the different types of hazardous movements we pick up on the right-hand side. And then you can see all the different people, all the different job positions. So this is for a couple of companies we work with. Here you can see housekeeping, they make a huge amount of hazardous movements per hour, up to 20. We've seen people in the 30s with housekeepers. And then you can see that as you go up the graph, the different people are making different types of movements or different quantities of movements as well. Now, anyone who's worked in a company that has these sort of roles will know that housekeeping gets injured a lot, unfortunately. The health and safety person doesn't get injured a lot. So it's a really good predictor of where your risk is, and then you're able to do something about it with the person. What else you can do? There's a mobile app, so we're giving the data back to them. It's all about engaging the person to make their own improvement. It's a really big part of our solution. We're not just collecting data so that you as a health and safety person can sit in an office and work with it, like I talked about in my engineering techniques, but we're actually feeding it back to the person so that they can start making their own improvement. The typical improvement we see is over a 2 or 3 week period that people reduce the number of hazardous movements they make anywhere from 30%. We see it up into the 50s, 60s. The best we've ever had was 90-something% improvement. So it's really cool. They're reducing their own risk of injury. So not only are you engaging them, but you're building a culture as well. You're collecting events that you're able to see on the analytics dashboard. So you're able to group again by workers. You're able to do your Pareto stuff that I talked about. You're able to see what types of movements, what types of job positions, and then you can move up the hierarchy of controls. So training, we are good at training, but we are really, really good admin control. But we're collecting the data that then lets you substitute, engineer, or hopefully eventually eliminate risk from your business. That's all available in our analytics dashboard. Yeah, we have 2 versions. I won't go through that. So how did we build reliability into our Soter products? So bathtub curve, what we have in our product, in the application that I showed you before, is we have specialized programs within that application. So some of the specialized programs we have are for new starters with our customers. So we actually build like custom content within the app. So that if you're let's say you're a new baggage handler and you're doing your induction, you get set up with our new starter baggage handling training program. You're wearing the device, you're getting the feedback. It's high quality training for the new starter so that you're giving them the best chance you can of building habits and techniques that are going to help them avoid injury for as long as they possibly can. The second program that we released a couple of months ago, which has been quite successful for us actually, is the early intervention program. So what we do with this program is we sell it to organizations, but they give it to their supervisors very often, so that when one of their workers has pain or says, you've built this early reporting culture, and you say, okay, now we've got to do something with these early reports. What you're able to do is set the person up with our early intervention program. So early intervention will explain why they're feeling pain, some rehab techniques that they can do themselves. This is not a recordable injury or a lost time injury or anything at this stage. So some things about what they can do themselves. We help them change the way they move a bit. And then the goal is that they fix the problem themselves and you never get a lost time injury. If we go into the Pareto rule, so collecting a heap of data. That then is able to be used by someone like yourselves on this webinar that is able to identify particular work groups, tasks, activities that cause the most risk. When someone does get injured, or when something, or when you say, okay, I actually want to do something about a particular incident, you've got all this data again that you can use and lean on. So better understanding of why something has happened, specifically musculoskeletal, because that's what our sensor does, but technology in general, whatever problem it's trying to solve, if you can use these big data sets to stop things from happening again, because you better understand why they happened in the first place. And then we get into our predictive analytics. So real-time capturing of data, big data sets, granular data sets, we know that can create better prediction models long-term. Yep, so we've got this is sort of our effectiveness rate. So when we work with companies for a year or more, this is the typical sort of number we see is 55% reduction in manual handling or musculoskeletal disorders. So yeah, but it does this because it's so scalable, it's high quality. We're feeding it back to the workers who make their own improvements and avoid their own injuries, which is good. This is the sort of industries that we work in. So I want to explain this because it's an interesting point, is that our sensor actually works, our solution itself actually works in all industries that have manual handling. And I was trying to figure out why that ended up working so well in all these different industries. And the reason I came up with was, as workers, we're making the same kind of movements that cause injury. The reason we make them is different. You know, the reason I make a movement in a mining company is going to be different to if I'm working in a warehouse. But the movement itself is usually the same. So we're able to apply our solution in a whole lot of different industries, which is cool. The other benefit of this is where Soter Analytics is becoming, we're creating a consulting company on the back of it, in that we're able to see what works in particular industries and share those with other industries. So if I look at a logistics company, there's things that our mining customers do that logistics can learn off. And there's benchmarking things we can do and all sorts of stuff. So with data, the whole system becomes smarter as well. All right, this is my last slide, and then we'll get into the Q&A. So I decided, like, let's make a special offer for everyone who wants to try a sensor technology. I'd love you guys to try ours, but you can try others as well. There's lots of sensor solutions out there. If you do want to try the Soter solution for avoiding manual handling injuries, this is the website that you can go onto. So soteranalytics.com, try Soter. Anyone who buys from this webinar, just send me an email, say that you're going to buy, that you're making a purchase, and we'll throw in a 1-month subscription as well. So if you want to keep my details, just take a screenshot of this page. If you want to reach out about anything, you know, like how to work with data, you know, you might not want to use our technology, fine, no problem, to be honest. If you want to make step changes in your safety culture with an organization that are data driven, then reach out as well. I have a good team, so we can help you with that, give you advice, all that sort of stuff. So that's the end of me talking. Although I'm going to keep talking, I guess. We'll do a quick Q&A. We're at the end of the time, so anyone who wants to drop off, like, that's fine. I'll go through the Q&A at the moment. I might need to stop sharing. Okay. Okay, so we have one question here. Can it tell if something is heavy? So yes, kind of. How our technology works is, I'll use the example again of lifting something off the ground. So first thing we're going to tell is we're going to see that the person is moving in a certain way. So if you guys can see my hand, you know, imagine this is the person. We can see if they're bending with their back, or we can see if they're using their legs, you know, putting all that force through their legs, keeping their back straight. So that's the first thing we're able to see. But we have, in our team, we have 4 data scientists. We're fortunate enough to, like, get quite a nice investment from investors that lets us invest in 4 data scientists. They're not cheap. What these data scientists have done with the data is, when you're lifting something, let's just say you're using a bad technique, we're capturing 60 data points a second, right? we're actually processing that data to work out what is the difficulty of that movement. Now, I'll give an analogy. If you guys have ever watched like a TV show or a movie or something where they're sipping coffee and there's clearly no liquid in the cup. And our brains can tell that, right? We're like, that's bullshit. There's no liquid in that cup. Something about that movement lets us know, lets our brain know that, okay, no liquid, no something, we're processing that. What we've done is the neural network or the data science sort of equivalent of that for lifting and moving movements. So the data is super heavy processed. We work out from that particular movement how long it took, how jerky it was, how far it went at the start, at the middle, at the end. These are 3 things that I can explain of the movement. There's like 48 things I think that I can't explain. So it's just data science. It's a black box neural network that we don't really know how it works. Even the data scientists don't know. But we've trained this model in a way that we've got people into our facilities making tens of thousands of movements. Our physio was classing all those movements as high intensity, low intensity. So this is the difficulty that I talked about, which then trained our network. So that what that means is when I'm a guy in the Pilbara wearing the device and I make a movement, that model is applied and it lets me know in real time, did I make a movement that was difficult, intense, hazardous, combined with a poor technique? I'm going to get a different kind of warning. And these warnings, they're longer, they're louder. I'm going to care more about them. I'm going to really, as a worker, make sure that I'm not making these movements. So to answer the question, do we measure if something's heavy? No. Do we measure if something's difficult? Yes. What are the reasons it's difficult? Well, it might be heavy. The worker might be fatigued. It might be awkwardly placed. There's a number of different things. Okay, we've got another question here. Has the tool or approach been shared with regulators to get their view on how it helps organizations meet their regulation and compliance requirements? It's a good question. We work in about 5 countries, but we work in the US, the UK, and Australia. So we've sort of made a bit of a decision in that we're not gonna, we have our customers working with regulators. And if a customer ever wants to apply a project and then get the regulator involved, we're good for that. We'd love to be involved. We're not actively trying to work with regulators ourselves. A couple of reasons. Firstly, logistically, it's quite difficult. Another reason is, to be honest, it's slow. We're like trying to make a solution as quick and as good as possible. And we sort of made a decision that if we get regulators involved, it's actually going to slow us down. So all we're really worried about is making a solution that reduces injuries. If regulators get involved at some point, perfect for us. We'll have no problems with that. We'll explain the technology. We'll even let them test it in detail. We've had universities and stuff test our software and our algorithms for accuracy. So we'll open the box with the right NDA in place, but we don't actively reach out to regulators to work with them. If there's no other questions, so we had 2 questions. If anyone wants to write a question, I guess do it. Yep, here we go. Okay, the system seems to be very technique-based. Training technique does not reduce injury risk. Bend your knees and keep the back straight does not reduce injury risk. For a whole lot of reasons, it's not effective and it's been proven in literature. Yeah, so it's a great question that I will just disagree with, to be honest. The reason for that is I've read the literature as well. Got to be careful how I word this. We have ridiculously big data sets. We have EMG sensor data from hundreds of thousands of movements that people have made while we're building our technology. We're measuring the muscle activity. We can see, like from our data, that if you bend your back the first time, what happens with your muscle activity. When you do it the 10th time, we see that your muscle activity is dropped, but more receptors are actually engaging. By the 100th movement, I've done the movements myself, I have pain in the back. So I think I'm trying to be careful on what I'm saying here because I don't want to like offend anyone. The research is good. It's just that we have a ridiculously big data set that we would love, if a researcher is out there and wants to engage us and work with that data set, very happy to. Training technique does not work. Yeah, okay. Show me the data. I'm a data guy. Show me the data. The literature reviews are okay. You know, there's a little bit of data, but show me a data set that is as big as the one that my team at Soter has built, and we'll see like if training technique can reduce pain and muscle fatigue particularly. I've got a chat section as well where people are asking questions, so we'll go into that. Yeah, one question is, how do trade unions respond to that technology? We work with a lot of companies that have unions. So at first we thought that is going to be a huge blocker for us, right? Like putting technology on people, measuring them, providing that all to someone sitting in an office. The first thing we have going for us is we're actually giving all the data to the worker themselves. So we're actually engaging the worker. It's not like this data is going somewhere that they don't understand. No, it's going to them. It's going to them in the beeping of the device. It's going to them in the app. So they actually get all the data themselves. So that's the first thing we have going for us. That usually gets the union over the line. We've actually never been blocked from a union, which is great. The second thing is that if there are still concerns, you know, from the more militant unions or the ones that don't trust that management is going to use this in the right way, that they're going to use this for performance managing older people out of the business or safety risks out of the business or whatever, then when it comes to our analytics dashboard, what we do for these organizations is we make all the data anonymous. So you're still able to see that the data is there. You're just not able to see that this was John and this was Bill. So you're not able to do that. If you can't see that data, you can't do anything with it. You can't performance manage if you can't see it and you don't know whose it is. And again, all the data going to the individual themselves. So that's how we overcome the trade union problem. I've got another question here. How do you get acceptance from employees? I can't get people to wear noise monitoring or other samplers. Do they feel they're going to be reprimanded? So I think I've basically just answered that question. When you're putting a noise monitoring system on someone, or let's say a dust sampling system, because I've worn them myself. They're bulky, they're annoying. When I'm driving in my car, it's against the seatbelt. It's not a great experience for me, and I never see the data. You know, no one ever tells me the data. I don't know if it's being used, what's happening with it. Well, if you come to our technology, it's super small. So you put it on the back of the shirt, you literally forget about it. So much so that you got to be careful you don't put it in the washing machine at the end of the day, because you do forget about it. So it's not creating any negative experience right there. Then you're getting feedback coming back to you. So you're actually getting the data yourself. You can do something with it yourself. That bit might get a little bit annoying, but we don't see it too often, that people just can't hack that. Like it's okay. They understand why they're getting the feedback and it's coming to them, so they're able to do something with it. So I think these principles that we've built into our product, and the fact that part of even the culture of Soter Analytics is we want to get the person, the worker themselves actually involved, are principles that then have a flow-on effect, a positive flow-on effect when people actually use our technology. And I think that's it. That's all the questions. Hopefully you guys have screenshotted my contact details if you want to know more information. If not, just go to the website, soteranalytics.com, and there's forms there that you'll reach me. Do encourage people to try some sort of technology in the workplace. In 10 years' time, like, it's not going away, this technology. So if you think about where careers will be in 10 years' time compared to where they are now, you know, more data, more technology, more sensors. So if you want to take the opportunity now to explore this world, we'll coach you through it and help you through it. So thanks everyone for attending. Thank you very much. Have a good evening.